All right, guys, so linear versus exponential growth. We're gonna go kind of fast today. I wanna keep this video as short as I can. We are covering quite a few topics, but they're small topics and a lot of it is stuff that you've seen in the past. So linear growth is like this blue line. That is a graphical representation of linear growth. Linear growth is when you grow by the same amount over time. So it's kind of like every week you get the same amount of allowance. So every week you increase by that amount of your allowance. Exponential growth is when you are increasing, when you're growing by a relative amount or by a percentage. And that's what this purple line is. That's exponential growth. It kind of looks like half of a parabola, which makes sense because parabolas quadratics have exponents, right? So as you notice the exponential growth, because you're doubling, on this graph in the number of years, the population in 14 years, the population doubled to 20,000. 14 years later, it doubled again to 40,000. 14 years later, it doubled again to 80,000. So exponential growth grows really quickly because of that doubling factor. Whereas if you're just growing by the same number of people every year, at 14 years, our straight town only has 15,000 people. So 14 years later, it's only grown by that same amount. So it went from 10,000 to 15,000. So after 28 years, it's only at 20,000. Okay, it's just growing by the same amount, not the same percentage. So a couple quick examples. The number of students at Wilson High has increased by 50 in each of the past 4 years. So every year they're increasing by 50. So part A is linear growth. And it says if the student population 4 years ago was 750, what is it today? Well, it's 750 4 years ago, and every year it has grown by 50. So that's 4 times 50, which is 200, which is 950 is our new population. Okay? The price of milk has been rising 3% every year. If the price of a gallon of milk was $4 a year ago, what is it now? So since we're rising by a percent, this is exponential growth. And we were at $4, but we're rising by 3%. So 4 times 3% is 4 times 0.03, which is $4.12. So the price of milk went up 12 cents. Now, next year, it's not going to go up 12 cents again because it's going to go up 3% of $4.12. So it's actually going to go up, 13 cents or so? So it's going to go up by more every year. C, tax allows you to depreciate the value of your equipment by $200 per year. If you purchased equipment 3 years ago for $1,000, what's its value now? So you're decreasing, and which is a lot the same as far as decay or decrease. Your graph is just, instead of going up, your graph is going down. So instead of going up, your graph is going down. Or instead of a straight line up, it's a straight line down. So since we're decaying $200 every year, this is linear decay. And we're going down $200. So 1,000 is where we started minus $200 over 3 years. So that leaves me with $400. Okay? Part D, the memory capacity of a state-of-the-art computer has been doubling approximately every 2 years. If a company's top-of-the-line drive holds 16 terabytes today, what will it hold in 6 years? So right now it holds 16, and every 2 years it doubles. So in 2 years, it's going to be at 32. 2 years later, it's going to be at 64. And 2 years later, it's going to be at 128. So in 6 years, you go from 16 to 128. All right, I think that's enough examples of those. We will talk about these parables when you come to class. We're also going to talk about folding paper and seeing how many folds it takes to get to the moon. But we'll do that one in class. So a few things that you need to keep in mind about exponential growth. Exponential growth leads to repeated doublings, like what we just saw with the terabytes. It went up by 16, then it went up by 32, then it went up by 64. With each doubling, the size of the most recent doubling is approximately equal to the sum of all the old doubles, which is kind of cool. When I get here, when I double, it's approximately what we had before. So when I double to 128, it's approximately everything else added together. So 64 plus 32 is 96. So 102, 112. So we're not exactly there because of that 16 we started with, but we're close. Exponential growth cannot continue indefinitely. After only a relatively small number of doublings, exponentially growing quantities reach impossible proportions. So these things grow really fast. If we were to continue with these terabytes, 2 years later, we're at 256, then we're at 512, then we're at 1,024, then we're at 2,048, then we're at 4,096. So you go from 16 to 4,000 in just 1, 2, 3, 4, 5, 6, 7, 8 terms. So it grows really, really fast. All right, doubling time and half-life. So to calculate doubling time, it's something that you're going to be asked to do. You're going to be given information, and it's going to ask you how long it takes for it to double. So after a time t, so t represents time in these equations, okay? After a time t, an exponentially growing quantity with a doubling time of t double. So big T double is how long it takes for a quantity to double, all right? It increases in size by a factor of 2 to the t divided by t double. Now, it doesn't look like this is a formula that you need to pull out because it's in the middle of a paragraph, but it is. So our increasing factor is equal to 2 to the t divided by big T. Okay, see, and that doesn't even look like an exponent. Let's rewrite that a little bit. Maybe, if my eraser will work. There we go. Okay, so we are doing 2 raised to the t divided by big T. Okay, so that gives you the factor that you're increasing by. Your new value, there's 2 equations right here. Your new value is what you started with initially multiplied by that factor. Okay, so to find out what your new value is, you take your initial value and you times it by this factor that we're going to come up with. So example 1 says that we are doubling with compound interest. So compound interest produces exponential growth because an interest-bearing account grows by the same percentage each year. So we know that this is not linear growth, this is exponential growth. Suppose your bank account has a doubling time of 21 years. So T double equals 21. By what factor does your balance increase in 50 years? So T equals 50. Now it didn't give me a starting amount, and it's only asking for the factor that I'm increasing by. So my factor is 2 raised to the little t, so 50, divided by big T, which is 21. So 2 raised to the 50 divided by 21. You'll plug that in your calculator, and it's going to give you the factor that you're increasing over 50 years, okay? Well, let's see. Do I have my calculator close? Here we go. So if we do 2 raised to the 50 divided by 21, we get 5.208, so 5.2. So our factor would be 5.2-ish, 5.21. So that's the factor that we're increasing. So if I knew what I started with, if I knew that I started with $50, then my new value, I would take that 5.21 and I would multiply that by my initial $50 that I started with. I would take $50 times it by 5.21 and end up with what? $260-ish dollars, something like that, okay? All right, world population doubled from 3 billion in 1960 to 6 billion in 2000. Suppose that world population continues to grow after 2000 with the same doubling time of 40 years. What would the population be in 2050? So I'm looking for my new population. I'm looking for my new value. So I take my initial value, which was, what, 6 billion? And I'm going to times that by my doubling factor. So 2 raised to the little t. Well, I'm going from 2000. Whoops, we don't want that. I'm going from 2000 to 2050. So that 50 goes on top because I'm going up 50 years. On the bottom is going to be my doubling time, and it took 40 years to double. So I would do 6 billion times 2 raised to the 50 over 40. So we can do that. We can do 6, let's see, that's 1,000, million, billion, times 2 raised to the 50 divided by 40. Nope, divided by. $50 divided by 40. Let's get rid of that. So my new population is, let's see, there's thousands, there's millions, there's billions. So we were at what, 14? That would be my new population in 40 years, or in 50 years. If I wanted to find out in 2200, well, 200 years has passed, so my time would be 200 because I'm starting in 2000. So I would do 6 billion multiplied by 2 raised to the 200 divided by 40. And I'll let you do that one on your own. All right, approximate doubling time formula. So now this isn't exact, but this is an approximation. So for a quantity growing exponentially at a rate of p% per time period, the doubling time is approximately, and that, see these squiggly lines right here? They don't say equal, they say approximately 70 divided by p, 70 divided by the percent. Now keep in mind that this works well, or best, I don't know how well it works, but it works best for small growth rates. And once you hit things that are growing by more than 15%, it really falls apart. It doesn't work very good, okay? So example 3. World population reached 7.5 billion in 2017 and was growing at a rate of about 1.1% per year. What's the approximate doubling time at this growth rate? So my approximate doubling time is 70 divided by my percentage, which is 1.1. So if I do 70 divided by 1.1, I get 63.636363. So my approximate doubling time is about 64 years. Approximately 64 years, okay? So if this was the growth rate that continued, what would the world population be in 2050? So I'm going to use that same formula. My new value equals my old value, so 7.5. And I go from 2017 to 2050. So that is, what, 33 years? And my doubling time is approximately 64. So I would do 7.5 times 2 raised to the 33 over 64. So if I do, what did we have? I forgot already. 7.5. Okay, 7.5 times 2 raised to the 33 divided by 64. So that's 10.7, which represents, so my new value would be 10.7, which was billions. I mean, you could put all the commas in the zeros, but I wrote it as 7.5 billion, so I can write my answer as 10.7 billion. Solving the double time formula. World population doubled in the 40 years. We did this. What was the average percentage growth rate during this period? What was the average percentage growth rate during that period? So if we doubled, if our doubling time was 40 years, and we use this approximation, then I would do 70 over a percent that I'm looking for. And it wants to know, what is that average growth rate? So I'm solving for x. So if I multiply both sides by x, let's see. Let's times x over here. Let's times x over here. Then I end up with 40x is approximately 70. And then if I divide by 40, x is approximately 70 divided by 40. So if I do 70 divided by 40, I get 1.75. So my population growth rate is approximately 1.75%. So I can find the percent using that same approximate doubling formula. Okay, exponential decay and half-life. So we are, after time t, if we're calculating half-life, now half-life is kind of like the opposite of doubling time. Doubling time is how quickly something doubles in size. Half-life is how quickly something decays over time, how quickly it gets cut in half. That's why it's called a half-life. So after time t, an exponentially decaying quantity with a half-life of t half decreases in size by a factor. So again, we have this formula that it almost hides in there. The factor that we're decreasing by is 1/2 raised to the t over big T half. So it's just like the doubling, but we're not doubling. We're not going up by a factor of 2. We're going down by a factor of 1/2. Okay? And then we can also use the new value. We can find the new value, just like we did with doubling time, if we know our initial starting value. So example 5, radioactive carbon-14. And this is where decay comes in a lot with radioactive materials, and that's what makes them radioactive, is because they are decaying. It has a half-life of about 5,700 years. So T half is 5,700. It collects in organisms only while they are alive. Once they are dead, it only decays. It's kind of cool. What fraction of the carbon-14 in an animal bone still remains 1,000 years after the animal has died? So because we're decaying, this factor can also be written as is also called a fraction of what we started with. Because we're not increasing, we're decreasing. So the fraction that what we're finding is the 1/2 raised to the t, which is our years, so 1,000 years, divided by our t half, which was 5,700 years. So I'd go to my calculator and I would put 0.5 raised to the 1,000 divided by 5,700. And if it gives me an ugly decimal, is it going to let me turn it into something nice? Nope. It's not going to be a very nice fraction, but we can write it as a decimal, 0.885. So the fraction that remains is going to be 0.885. That's my remaining amount of what I started with, okay? So suppose that 100 pounds of Pu-239 is deposited at a nuclear waste site. How much of it will still be present in 100,000 years? I'm assuming that it wants us to use the same half-life because it doesn't give us a half-life. So let's assume that our T half is also 5,700 years. I don't know why it doesn't give us that, but our initial value, so we're looking for how much is still present. So our new value is what we started with, 100 pounds, and we're going to times that by 1/2 raised to the 100,000 divided by 5,700. Okay, so we're going to do 100 times 1/2 raised to the 100,000 divided by 5,700. So there is going to be 0.0005 pounds left after 100,000 years. So less than a pound, but we only started with 100, and it's been 100,000 years, but there's still some of this material that's left over Even after 100,000 years, we still have some of it left behind. Now be really careful when you're using these formulas. Your t and your t half, I should make that a capital T. Your t and your t half, or your t and your t double, you've got to be really careful that those are in the same units. So if t is in years, your t double needs to be in years. Okay, you can't put one in years and one in centuries or something like that. So approximate half-life formula, just like the approximate doubling time formula, we can approximate when we have low percentages. So the approximate half-life is 70 divided by the percentage. It's exactly the same as it was before. So suppose that inflation causes the value of a Russian ruble to fall at a rate of 12% per year relative to the dollar. At this rate, approximately how long does it take for the ruble to lose half its value? So we're looking for the half value, our half-life. So I do approximately 70 divided by 12%. So I'm going to do 70 divided by 12, and I get 5.833333. So my half-life is approximately 5.83, and that 3 repeats. So in about 5.8 years, half of the value is going to be half as much as it was when we started. It's going to take almost 6 years for the value to go down half. Okay, couple more. Exact doubling time. Now I know the video's starting to get a little bit long. We decided we're doing A and B together because we might as well. You're doing the homework together. The exact doubling time formula. So instead of using an approximation, the exact formula uses logarithms. And we'll maybe get into that at some point, how that comes about. But the exact doubling time is log base 10, 2 divided by log base 10 of 1 plus r. And r is the fractional growth rate. Okay, it's our fractional growth rate. So the units of time used for the double and r must be the same. Okay, for example, if the fractional growth rate is 0.05, then the doubling time also will be measured in months because the 0.05 is measured in months. And then we have something similar for exact half-life. So when an exponentially decaying quantity, the fractional decay rate r is negative, r is less than 0, the half-life is. So we're decaying when our rate is negative, right? Okay, so large growth rate. A population of rats is growing at a rate of 80% per month. Find the exact doubling time for this growth rate and compare it to the doubling time found with the approximate doubling time value. Okay, so the exact doubling time is equal to log 10(2) divided by log 10 of 1 plus our rate, which is 0.8. Okay, I'm going to write it as a decimal, 1 plus 0.8. So when I put that in my calculator, first of all, I'm going to make a fraction bar. And on top, I'm going to put log, and your log button's right here on your calculator, log, and it automatically does base 10, so you don't need to worry about putting the base in. But I'm going to do log 2, and then I'm going to do log of 1 plus 1.0, no, 1.8, right? 1.8, because it was 80%. So log 2 over log of 1 plus 1.8. And I get 0.6732, a great big long decimal. So it's exactly 0.6732 something, 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 something. If I were to estimate, if I were to use my estimating formula, I would do 70 divided by my percent. 70 divided by 80, which is approximately 70 divided by 80, 0.875. So if I look at those two, I mean, relatively, they seem close together. They're both decimals. But this 0.875 is like a third bigger. It's 1/3 bigger than our exact doubling time formula. And remember that it said the approximations don't work very well when you have percentages bigger than 15. And we're using 80%, which is a lot bigger than 15. So that makes sense why that one wouldn't be a very good approximation. Okay, so from here, you've got homework 8A and homework 8B. Okay, again, I know the video ran a little bit longer, but we covered 2 homeworks at once. They're pretty similar, so I think that's okay. I think you'll survive. When you come to class on, probably not Friday, because we're going to be taking the test, a lot of you on Friday, but on Tuesday next week, we'll talk a little bit about these parables that have to do with doubling time and exponential growth. We'll talk about he wrote a headless. We'll talk about the magic penny, and we'll talk about folding paper to reach the moon, which turns into a pretty cool conversation. So we'll see you then.